Welcome to lecture 1. In this lecture, we will briefly discuss about the working principle of synchronous generator. The working principle for any generator is same and it is also similar to what we will discuss today. The concept has been discussed in the book of Concept of Physics by Verma, and we will start with that. I hope all of you have studied it in class 11th or 12th. Now let's consider a loop placed in a uniform magnetic field. So when we say that it is placed in a uniform magnetic field, we say that there is a magnetic field which is perpendicular to the plane of the paper. Let's say that the magnetic field is like this. That is, this symbol indicates that the magnetic field is coming from the top and going into the plane of the paper. It is something like this. So there is a uniform magnetic field, and in this uniform magnetic field we have placed a loop. Now the question is, what is the EMF induced in this? So for this we have to first find the flux linkage with this coil. So how we find the flux linkage with this coil? The flux linkage with this coil is equal, phi is equal to B dot A, where all these are vector. That is the dot product of the flux density B and the area A. Now area is taken as a vector here, and to find the direction of the vector we have to take a sense of rotation. That is, if you assume that we are traversing like this, then we will curl the finger like this. This thumb will give us the direction of the area vector. However, if we traverse like this, that is, if you take the loop in this way, then we will curl our finger like this, and the direction of area vector will be along this, will go downward. So this B dot A, it will be a dot product, so we can write it like this: B A into cos of theta. What is cos of this theta? Cos theta is the angle between the vector B and the vector A. The direction of B is from top to bottom, and the direction of area vector, we will see how it will vary. Now this is the loop which represents a coil. Now this coil, if we consider this scale to be the coil, then the coil is rotating like this in this direction. That is, here the angle is 0, it rotates like this, and now the angle is 90 degree. Now it is more than 90 degree, it is rotating, and now it is 180 degree. It's like this. Now let's say if we consider the direction of this area vector to be downward, that is inside the plane of this paper, then this edge of this one points the direction of the area vector. So you see that as it rotates, the area vector also changes the direction. So when the conductor rotates in a uniform magnetic field, the area remains the same, the flux density remains the same. What changes is this theta. As a result of this change of this theta, the flux linkage with the coil changes. That is, this phi, which is a dot product of B and A, this phi changes. So the flux is given by BA cos theta, and we all know that from Faraday's law of electromagnetic induction, induced EMF E is equal to minus d phi dt. When I write this, I assume that there is only one conductor. If there are number of conductors, then it has to be multiplied by the number of conductors. So this is equal to minus d dt of phi. Phi is B A cos of theta. Now B and A, both of them are constant, so we can write this as minus B A into, what is the derivative of cos theta? minus sine theta into d theta dt. What is d theta dt? Theta is the angle, rate of change of angle is the angular velocity. So minus omega into b into a is nothing but flux into sine theta. So there, this will be plus. This minus and this minus will make it plus. So if there are n number of turns in this coil, so it will be n phi omega into sine theta. We can write it as omega t. Now whatever we have said that this is working principle of synchronous machine, to be more appropriate, this is the working principle of any machine that generates some voltage. In DC machine also it works like this, in synchronous machine also it works like this. Now what we can do little bit more in this is like to see how the same thing graphically. That is, here if you see it's a cos function, so this represents theta equal to 0, this is theta equal to 0, so this is how my flux is changing. It's a cos function, so it started from maximum, then 0, then negative, and this is how, this is my flux, this is my flux. Fine. For this change of flux, why this change of flux is there? The flux produced, this B is constant, but the change of flux linkage is due to the rotation. That is, when I am rotating like this, this area vector and the angle between the area vector and the B is changing, and for this cos theta is coming into picture. So it's not that the B is variable, but the angle between B and A is changing. Now for this change in flux linkage, there is the induced EMF in the coil, and this is given by n omega phi into sine omega t. Now from this we understand one thing, that the induced EMF lags the flux by 90 degree, or the flux leads the induced EMF by 90 degree. This will be useful while drawing the phasor diagram, and in the previous set of lecture, starting from this, we have drawn the phasor diagram. So you can refer to lecture 9 of the previous lectures, and you can find that we started from this and then we draw the phasor diagram. So what we have to remember here is that the air gap flux leads the voltage by 90 degree. It happens in all machines. So whatever we have discussed, it is not applicable to synchronous machine only, it is applicable to all machine. And what is more important is that you have already studied it is in class 12th. So there is nothing new in that, we have only revised what you have studied in class 12th. Now here the direction of flux in this diagram is from top to bottom, and the coil is placed in this plane of paper. It is easy to understand here how this theta is changing, or how the angle between the area vector and this flux is changing. In books of electrical machines, the diagram is drawn in this way. Here what we say is that this is my rotor, in this the conductors are there, and this is my field, or the member that produces the flux. It can be stator, whatever it is the field. Now it will be difficult from here to visualize that the flux linkage with this conductor is maximum here and minimum here, because if I assume that the conductor is rotating like this, I can understand that the flux lines are passing through this, but when it comes here, I fail to understand why the flux linkage is 0. I find it a bit difficult for me to realize that the flux linkage with the conductor is changing. So just to give you a clear picture, I have gone to class 12th and explain it. The same thing happens here. The phenomena is happening in a 3D, so it is not possible to draw the whole picture in a single diagram. So this is one view and this is another view. Here the flux is coming from top to bottom. Here the flux is coming like this in the plane of the paper. Here the flux is in the plane of the paper. Here the flux is perpendicular to the plane of the paper. Otherwise the concept is same. Now let's look at this diagram. We will explain the same thing once again, hoping that it will make the understanding of the machine little bit more clear. So here what we have assumed is that there is a rotor that is rotating in this direction like this. This is clockwise rotation, though most of the books take an anti-clockwise direction. But there is no harm in taking the rotation to be in clockwise direction. So let us assume that the machine is rotating like this, and this is my north pole and this is my south pole. How this north pole and south pole is created? Definitely by passing a current through the pole. So if it has to be a north pole, it means that the direction of flux has to be like this. So if you curl your finger like this, it is giving like this. So the current will enter through this and it will come out through this. Here also it will be like this. To find the direction, how to find the direction of this current and field, it has been elaborated in the previous set of lectures. You can always go through this and it will be really helpful. Now when it is rotating like this, say at this point I call this member to be R, this end of the coil to be R, and this end of the coil to be R dash. Okay, now here you can see that the induced EMF in this conductor will be 0. Why the induced EMF will be 0? The flux linkage with this conductor is maximum. Here what we are saying is exactly the similar situation here. Here the coil, this is my coil which is placed like this. So the flux linkage of this will be maximum because theta is 0, cos theta is 1, and hence the rate of change of flux linkage, that is induced EMF, is sine theta. So for theta equal to 0, this will be 0. So this represents a condition where theta is 0. Now for theta equal to 0, the induced EMF is 0. So I have not given any direction here. Let's come to the next location. Here this coil after some time has come here. So this has remained as R and this is R dash. How to find whether it will be cross or dot? How to find that? You have to apply Fleming's right hand rule. So what does the rule state? Rule states that the first finger should point to the direction of field, this finger should point to the direction of rotation, then this finger will give you the direction of induced EMF. If you apply this rule here or here, it will be easier to apply it here. Then you will find that it will be a cross here and it will be a dot here. Cross means inside, the magnetic field is going inside. What are the direction? This is the direction of field. It is coming from north pole to south pole, and this is the direction of rotation like this. So my first finger should point to this, my thumb should point towards this, then this finger will go like this and it will give me the direction of induced EMF. Once I find for this location anything above this line, this is my 0, this is my 0 voltage. So anything above this line will have a cross and anything below this line will have a dot. So this will be cross, this will also be cross. You can apply and find out that. If you have any doubt regarding this, please refer to the previous set of lecture. Now after some time it will come here again. At this location also, this is above this line, 0 line, so it will be a cross, it will be a dot. If you come here, now this is my R and this is my R dash. It has rotated further. Now here it will be R, it will be R dash. Now you see that this R has come below this line, so it will be a dot, it will be a cross. After some time it has come here, so it will be R, it will be R dash, it will be dot, it will be cross. So if you measure the voltage by connecting a voltmeter, say between R and R dash, let's say that we call this potential to be positive, this one to be negative. There is no harm in calling opposite way also, but let's say that take a nomenclature that I take cross as positive. So at this location the potential is positive, here it is positive, here it is positive, but when you come here at this location, R is negative with respect to R dash. Here also R is negative with respect to R dash. So we see that if I measure the potential between R and R dash, sometime I get a positive potential, sometime I get a negative potential. That is, I get a alternating voltage. Alternating means sometime it will be positive, sometime it will be negative. Now let's repeat our previous exercise. For this location, my induced EMF, the flux linkage is maximum. Here it is reducing. Here this point corresponds to this one. Let's call this as A, this as B, this as C, this as D, this as E, this as F. So this represent A, say this represents your B, this represents your C. Then if you come here, this represent your D. Now this is negative maximum, D is positive. Here the flux linkage is still positive. Okay, this is your E and this is your F. Okay, now let's draw this once again. And corresponding to this will be the induced EMF. This is exactly the same thing that we have discussed previously, that my flux linkage is varying cosinusoidally, and accordingly my induced voltage, which is rate of change of flux linkage, is varying sinusoidally. So whatever we have discussed here mathematically from here to here, we are explaining the same thing graphically. Here we have mathematically derived it and then draw a graph. Here we are trying to explain the same thing graphically and draw the same graph. Now this is a single phase generator. What happens if I put one more coil, that is one more set of coil? Let's say that I place another coil that is behind this. Now what is behind in a round thing? To find the behind, we have to know the direction of rotation. This is the direction of rotation here. So if this is the direction of rotation, then behind means in this direction. That is, this is the direction of rotation, so anything on before this is behind. So this is my Y. Let's say that this is my Y phase, and let's call it as Y, and the opposite to that is Y dash. So Y dash will be cross. Why Y dash is cross? Because it is above this 0 line and this is dot. So if I have assumed that if R is cross, I take it as positive, and if R is dot, I take it as negative. This is what I have assumed. So for Y also this will hold good. So y is dot means y is negative. Okay, we will see that. Now, what is the angle between r phase and y phase? This is the angle. This is in space. This angle is mechanically 120 degree. If this angle is 120 degree, then I will get a voltage that will have a phase difference of 120 degree in time here. Okay, let's see this. Now, as the y phase, after some time r has come here, so y will come here. This will be dot, this will be cross. When r will be here, y will be here. This will be dot, this will be cross. If r is here, y will be here. Now, assuming that it is above the zero line, this will be cross and this will be dot. Here y will be cross and this will be dot. This is y, this is y dash. This is y, this is y dash. This is my y, this is my y dash. How I am marking y and y dash? Y will be behind r by 120 degree. This angle will be 120 degree. So, if y phase is placed 120 degree behind r and it is also rotating in the same magnetic field, then this coil will also induce a voltage. So what will be the magnitude of this induced voltage? It will lag the r phase voltage by 120 degree. So this is the voltage, this is the voltage between r and r dash. That is voltage measured between this end of the coil and this end of the coil, this end of the coil and this end of the coil. This I am taking as positive and this I am taking as negative. That is, this is connected to the positive terminal of the voltmeter and this is connected to the negative terminal of the voltmeter. Now, if I connect a voltmeter between this terminal and this terminal, this is connected to positive terminal and this is connected to the negative terminal, then I will get a voltage waveform like this. V, Y, Y dash. It will also be a sinusoid. Why it will be a sinusoid? Because it's also a coil. It is also rotating, so the area vector will vary cosinusoidally. So the induced voltage will be sinusoidal. The only difference is that the location is 120 degree behind, so the voltage will lag this voltage by 120 degree. Lag the voltage means what? This is the zero of r phase. The zero of y phase will be behind this by 120 degree. So it will reach zero after this by a time equivalent to 120 degree. Now let's look at B phase. Where will be B phase? B phase will be behind Y phase by 120 degree. So this is Y phase. B phase will be behind this Y phase by 120 degree. So B phase will be somewhere here. So this will be B, this will be B dash. So this is B dash, this is B. So whether this will be a cross or a dot, this will be a cross because it is above this zero line. After some time, what has happened? R has moved here, so R has come here, Y has come here, so B will be here. This will be my B. Whether it will be a cross or a dot, assuming that it is above this zero line, this will be a cross and this one will be a dot. Similarly, after some time, this will be my B. Why it will be B? Because this is my R phase. Y phase is behind this by 120 degree. This is 120 degree. And B phase is behind this one by another 120 degree. So this is my B. And the opposite end of this is B dash. Sorry, this is B dash. Okay. So this will be a dot, this will be a cross. Here, if you come here, this will be R. 120 degree behind this is my Y phase. So this is 120 degree. And 120 degree behind this is my B phase. So this is my B phase. So this will be B and this will be B dash. This will be a cross, this will be a dot. When it comes here, this is Y and 120 degree from Y is my B. So this is my B and this is my B dash. It will be a dot here, it will be a cross here. Why it will be a dot? Because it is below this zero line. If when it comes here, this is R, 120 degree behind R is my Y. So this is my Y, this is my Y and this is my Y dash. So this is a dot, this is a cross, and 120 degree behind this Y face, this is my B and this is my B dash. So this will be a cross and this will be a dot. Now if you draw the voltage corresponding to this, if you draw this voltage corresponding to this, what you will see that here corresponding to this B will be positive. Why positive? Because B dash is having a dot and B is having a cross. So it will be like this. So how many set of coils we have placed here? We have placed 3 sets of coil and these are displaced by 120 degree. They are placed in the same magnetic field and they are also rotating in the same speed. That's why the magnitude of the voltage induced by each of them are same. They are same because we assume that all of them have same number of turns. This is an assumption which is very valid. Then another, they are placed in the same magnetic field, okay, and they are rotating in the same speed. That's why the magnitude of induced EMF, which is given by this, number of turns is same, flux, it is placed in the same magnetic flux, so flux is same, this omega, there is speed of rotation, that is same, so the magnitude of the induced EMF is same. What is difference is that somewhere it is sin omega t, somewhere it is sin omega t minus 120 degree, somewhere it is sin omega t minus 240 degree. So if we call the voltage across R phase, VR is equal to Vm sin omega t, then the voltage across Y phase will be Vm sin omega t minus 2 pi by 3. 2 pi by 3 is nothing but 120 degree, and voltage corresponding to this B phase, what we call it as VB, is equal to Vm sin omega t minus 4 pi by 3. 4 pi by 3 is nothing but 240 degree, which is the angle difference between R phase and B phase, called this angle. This is 240 degree from here to here. and from here to here it is 120 degrees. So what we have seen is that how three phase is generated in a synchronous machine. We have placed three coils, that's why three phase voltage is generated. However, if you place 5 set of coil, it will generate 5 phase of voltage. If you place 6 set of coil, it will generate 6 phase of voltage. If you place n number of sets of coil in the armature, then it will generate n phase voltage. Whatever we have discussed in this lecture is from the book of S.K. Bhattacharjee, and I will insist that you please read this book. That is very nicely and very easily elaborated. We will continue this set of lectures following S.K. Bhattacharjee. Thank you. We'll meet in the next class again.